The Big Theorem is probably the most important theorem about sequences that you will learn in a calculus course. It helps us compute many limits very quickly. In this video, I will explain the statement of the theorem and how to use it. In the next video, I will write a proof. As motivation, let's look at a type of limits that we understand very well: rational sequences. For example, let's say I need to compute the limit as n approaches infinity of n cubed plus 2n plus 1 over 5n cubed plus 3n squared. You probably know how to do this. When I have a quotient of polynomials, the only thing that matters is the biggest power. In the numerator, the biggest power is n cubed. In the denominator, the biggest power is also n cubed. So this is the same as the limit of n cubed over 5n cubed, which is 1/5. That is the quick calculation. But let's remind ourselves of why this works. To justify this method, the trick is always to factor the biggest power. Let's factor n cubed in both numerator and denominator. I can cancel these terms, and let's see what we have left. As n approaches infinity, 1 over n squared has limit 0, and so do 1 over n cubed and 1 over n. Now use the limit laws, and that is how we get 1 over 5. The key observation here is that the limit as n approaches infinity of n over n cubed is the limit of 1 over n squared, which is 0. And the same is true for the limits of the other quotients. And that is why, when I have a sum of an n cubed term and an n term, the n term is irrelevant, and the n cubed term determines the answer. The same happens with the other irrelevant terms. This is useful. Can I generalize it? I would like to do the same thing with other sequences, not just powers. I want to compare other terms and decide which ones are more important and which ones can, so to speak, be ignored when added together. That's what the Big Theorem is about. First, I need a new definition. We will use this new concept only for positive sequences. I am going to write that a sequence an is less than a sequence bn to mean that the limit of an over bn is 0. This is just new notation. And when this happens, I am going to say that an is much smaller than bn, or that bn is much larger than an. For example, with this new notation and definition, I can say that n is much smaller than n cubed, because the limit of the quotient is 0. Now I have the tools to state the Big Theorem. The Big Theorem establishes a hierarchy among sequences. It says that a logarithm is much smaller than any power with positive exponent, which is much smaller than any exponential with base greater than 1, which is much smaller than n factorial, which is much smaller than n to the n, which I will call a power exponential. That's the Big Theorem. Why is this useful? We can use it to compute many limits quickly. Let's look at an example. I want to compute the limit as n approaches infinity of e to the n plus 2n to the 100 over ln n plus 5e to the n. According to the Big Theorem, n to the 100 is much smaller than e to the n, and ln n is much smaller than e to the n. So the only terms that matter are e to the n and 5e to the n, and this limit is 1 over 5. That's it. Why is this? We can justify this rigorously from the Big Theorem, like I did in the example at the beginning of the video. To justify this, I will factor the biggest term, in this case e to the n, in both numerator and denominator. And let's look at what I have left. N to the 100 over e to the n has limit 0 as n approaches infinity. That is exactly what the Big Theorem says. The same applies to ln n over e to the n. Now use the limit laws, and we get that the full limit is 1 over 5. That's it. I hope you can see from this example that there are many other limits that we can compute very quickly using this theorem. Of course, we still need to prove it. The proof will be in the next video.